In this video, I want to introduce the idea of a linear system, or a system of linear equations. And in doing so, I hope that I will answer the 5 questions that are on the screen. So first of all, what is a linear equation? You may think you know what a linear equation is, but maybe you haven't thought about what a linear equation means in higher dimensions. What is a linear system, or equivalent terminology, a system of linear equations? Then I want to give some visual ways of thinking about this. I want to look at graphs of linear systems when we're in 2 and 3 dimensions where we can actually visualize these things. And then I want to kind of take a bit of a turn and look at this notion of a solution to a linear equation or a linear system. So in particular, what is a solution to a linear equation or linear system? And how many solutions can a linear system possibly have, given some small amount of information about it? So I think the place to start is 2 dimensions. So I want to look at linear equations in 2 dimensions. And I think that the first place that almost everyone sees a linear equation is in their first algebra class, and that equation looks like y equals mx plus b. So something like y equals 2x minus 3. And this is a linear equation. I'm not gonna come in and say that this no longer counts as a linear equation. Let's look at a graph of this. So it has slope 2 and y-intercept -3. And so I'll put this up onto this graph in Desmos. And yeah, this is the graph of a line. So hopefully nothing shocking or surprising so far. But we have other linear equations. So let's look at a different one. Let's look at this. I'll write this a little differently. So I guess this is a little bit different. 4y minus 2x equals 9. So this graph in blue, when I graph this, let's get rid of this one. Notice I get a straight line again. And hopefully this is not surprising. You can convince yourself, oh yeah, I could rewrite this thing as y equals mx plus b. But there's a third example that I want to give that I think highlights that maybe the y equals mx plus b thing isn't a great way to write linear systems. So what about this equation? X equals minus 3. So you may recall this when we have an equation like x equals minus 3, that's going to be a vertical line where all the points are -3. But this is still a line, and this still counts as a linear equation. And so it turns out that writing a linear equation always like this is not a good idea because you can't take this equation and rewrite it like y equals mx plus b. So in general, what we'll do is we'll write these linear equations like ax plus by equals c. This will be generally what a linear equation in 2 dimensions looks like. And go and convince yourself that all 3 of these, if they're not already in that form, can be rewritten as ax plus by equals c. And they'll all have graphs that are lines. So let's put them all up at the same time. We have these 3 linear equations. Their graphs are all straight lines. All right, so that's linear equations in 2 dimensions. So let's bump things up. Let's bump it up to 3 dimensions and look at what linear equations look like in 3 dimensions. And maybe it's worth, if you haven't seen this before, just take a moment to, guess. What do you think the linear equation is going to look like in 3 dimensions when we graph it? So following along with what we did before, I'm going to write down some linear equations, but I'm not going to mess with how they look. I think I'll write down a few examples, and you'll see that that pattern of ax plus by equals c that we had in 2 dimensions will naturally extend to 3 dimensions when we're trying to think about what would an equation of a linear system look like. So the first one I'm going to look at is x minus y plus z equals 4. And again, think about what this might look like, and then I'm going to graph it. And we just have kind of part of the 3-dimensional coordinate system, but you can see that this is a plane. Hopefully you can see that, right? If I get it at the right angle, it kind of disappears. It's a flat plane. Stop it from spinning there. And I want to give a second example because I think maybe you might already, if you hadn't already guessed, you might be saying, oh yeah, that makes sense. These should probably just be planes. But let's look at one more just to see if our intuition is right. Minus x plus 2y plus 3z equals 2. Let's look at this graph. And again, we got a plane. We got a different plane, but it's still a plane in 3 dimensions. And this will generally be the case. So when we're working in 3 dimensions, our general format will be that our equations look like ax plus by plus cz equals d. And our graphs will be planes. Okay, 2 dimensions covered, 3 dimensions covered. Let's kick it up a notch. Let's look at linear equations in higher dimensions. And I'll just use 4 as an example, but what I say, hopefully in 4 dimensions, you'll see how that would translate to anything higher. And if you're expecting me to switch screens to the Desmos 4D graphing calculator and totally blow your minds with visualizations of 4-dimensional linear equations, I'm sorry, I think you're going to be a bit disappointed. So I'm not going to attempt to graph this, right? I'm just linear equations in higher dimensions. I don't know how to directly visualize this. I'm not convinced that anyone does. We'll see in this course, there are lots of ways to get insight from visualizations, but it's not going to be by somehow producing a 4-dimensional graph. But we can still talk about what these things look like. And I want to write down an example of a linear equation in 4 dimensions. So a linear equation in 4 dimensions might be something like 3x1 minus 2x2 minus x3 plus 5x4 equals 8. That's an example of a linear equation in 4 dimensions. And in general, it would be something like a1x1 plus a2x2 plus a3x3 plus a4x4 equals b. And if you look at this and wonder, okay, why are we switching from x, y, z to x1, x2, x3, x4? Maybe you start to see ahead that I went up from 3 dimensions to 4 dimensions because that's the next spot to go. But ultimately, we want to talk about linear equations in 1,000 dimensions or something like that. And this sort of general way of writing things, ax plus by plus cz equals d, is a bit short-sighted. It doesn't naturally allow us to talk about higher dimensions. And so instead, using subscripts on both our variables and our coefficients is a nice way that we don't have to start using W and then deciding, well, what letter's next? What if I go to 5 dimensions, what should the 5th letter be? We won't have to do that. We'll just use subscripts. So I mentioned that we're not going to actually be able to directly visualize something like 4 dimensions, but what we'll discover in this course is that oftentimes when we're dealing with higher dimensional problems, we can gain a lot of insight into them by, in some sense, pretending they're 2 or 3 dimensional problems and drawing a picture in 2 or 3 dimensions. And that picture will hopefully give us insight into how things are going to work. And we then go and verify that that actually works, right? We should never totally trust a picture. We should especially not trust a picture when we know that the picture is wrong, right? When we've drawn an example of a linear equation in higher dimensions in 3D and kind of assumed things would work. And so what I mean by that is, if I'm dealing with this equation, this 4-dimensional linear equation, and I'm trying to visualize what it is, this is how I visualize it. I visualize it as a plane in 3 dimensions. But in the back of my mind at all times, I remind myself, look, it's not actually a plane in 3 dimensions. And so just because something looks like it's true, that's good insight. And maybe that gives me some indication that it might be true. But I want to go and verify that it actually is true. So we'll still visualize stuff as we get into higher dimensions. We just won't be quite as trusting of what we see. Okay, so we've defined linear equations in all dimensions. And we've looked at graphs in 2 and 3 dimensions and talked about how we can visualize graphs in higher dimensions by just pretending they're in 3 dimensions or 2 dimensions. Now I want to talk about solutions to linear equations and linear systems, and so I want to reset all the way back to 2 dimensions. So let's go back up for linear equations in 2 dimensions. And in order to, I'm going to erase a little bit of this because I don't want all of this here. I want to just start with my line y equals 2x minus 3. A solution to this linear equation is a set of values of the variables that make the equation true. And so, for example, if I make x equal 2 and y equal 1, we can see that 1 equals 2 times 2 minus 3. Or in other words, 1 equals 2 times 2 minus 3. So a solution is just a set of values of the coordinates that make the equation true. And in terms of a graph, when I put the point 2, 1 on the graph, x equals 2, y equals 1, that point lies on the graph. So the graph of a linear equation is actually just all of its solutions. That's really what that means. So this point would be written 2, 1. So that's a solution to a single linear equation in 2 dimensions. Let's go up to 3 dimensions. And in 3 dimensions, it should be basically the same thing, I would hope anyway. That is, if I look at this plane here, this x minus y plus z equals 4, and I'm thinking of this equation and I want to know its solutions, one solution is 1, 1, 4. Point 1, 1, 4, because if I plug these values in, if I plug in x equals 1, y equals 1, and z equals 4, I end up with an equation that's true. And on the graph, as we hope, when I put this point here, you can see up near the top, this blue point, this is the point 1, 1, 4, and it does in fact lie on the graph of this linear equation. So this plane, the graph of the linear equation, is just all of the solutions to the linear equation. And the same would be true in higher dimensions, right? A solution is just a set of values for all the variables that makes the system, makes the equation true. Okay. So what's a linear system? We've talked a bunch about linear equations. What's a linear system? Well, a linear system is just a collection of linear equations. So let's go back to 2 dimensions. I actually have a linear system written down right here. When we're thinking of both of these equations not as separate things, but as 2 equations that are collectively being considered at the same time, this is a linear system. So a linear system just refers to one collection of one or more linear equations. And a solution to a linear system is a set of values of the coordinates that make all of the equations true. So a linear system consists of not necessarily just one, but potentially more than one linear equations. And a solution is a set of values that makes all of the equations true. Missed an S there. So looking at this linear system, still have this point on the graph for some reason. What's a solution to this? Well, one solution is 3.54. So that is x equals 3.5, y equals 4. Now, why is this true? Well, you can just confirm on your own. If I plug in x equals 3.5, I get 7 minus 3, which is 4. The equation is true. Now here, 4 times 4 is 16, minus 2 times 3.5 is 7, is 9. So this is a solution to the linear system. Let's look at the graph. This was y equals 2x minus 3. This is 4y minus 2x equals 9. And if I draw this point, 3.54, this point is at the intersection of this linear system. So in fact, this is the only solution to the linear system. It's the only value that makes all of them true. Let's look at 3 dimensions. So in 3 dimensions, again, I have two linear equations. X minus y plus z equals 4 and minus x plus 2y plus 3z equals 2. And I found a solution, but you can confirm for yourself, I found a solution just to the first equation. This does not work here, right? If I plug in x equals 1, y equals 1, z equals 4, and calculate the left-hand side, I don't get 2. All right, so are there any solutions to this linear system? It's not obvious that there should be, but there is. So one solution is the point 0, minus 2, 2. Or in other words, x equals 0, y equals minus 2, and z equals 2. And I recommend confirm for yourself that when I plug those values in for x, y, and z, I get both equations true. Let's look at the graph. And maybe pause and think to yourself, what do you think is going to happen? So here are my 2 equations graphed. Where is the point 0, minus 2, 2 going to fall? We can see this orange point right here. It falls in the intersection of the 2 planes, which matches up with what we saw in 2 dimensions. But here we have this additional thing we can notice, which is that the planes, when you intersect 2 planes, if they intersect in a line. And so there are actually more solutions to this linear system. So the solution set, which is the set of all possible solutions, is the line of intersection. That line where the 2 graphs intersect tells us all of the solutions to this linear system. So we saw that in our 2-dimensional example, we had 2 linear equations and they intersected in a single point. And this corresponds to the fact that there's only one set of values for the variables that makes both equations true. And in 3 dimensions, when we had a simple linear system with just 2 equations, we realized that, oh, well, they actually intersect in infinitely many points. They're graphs, and so there are infinitely many solutions. What if I add to my system a 3rd equation? So what if I add the equation, let's see if I can make these fit on this screen without erasing anything. What if I add 2x minus 3y plus z equals 8? Let's remove this solution. Well, so now when these intersect, I've added this plane, we can see if we kind of move this around that they seem to intersect in a single point. And I had actually chosen this point earlier. It's this point 0, minus 2, 2. And so now I'll get rid of this bottom line. Now that I've added a 3rd equation to my system, if I have this system of 3 equations, I actually do have exactly one solution. Okay, so this raises a question, which is the final point I want to make, which is how many solutions can you get from a linear system, right? So we've seen examples where we had infinitely many solutions. We saw an example where we had one solution. And what's left is it possible to have no solutions to a linear system? And is it possible to have some other finite number of solutions? So could you have like 2 solutions to a linear system? And I want to summarize this by looking at 3 dimensions. What I'm about to say is true in all dimensions. That is the number of possible linear systems. But I think we're best served not worrying about trying to justify it for all of them. So how many solutions? And I don't know why I scrolled down there. That wasn't what I wanted to do. I think what I want to do here is not worry too much about what these equations are, but just worry about the pictures. So what I'm doing is in 3 dimensions, but let's look at an example. We've already seen a few examples of this, but let's look at an example of infinitely many solutions. This is the one we looked at. So in 3 dimensions, we can have our planes intersect in a line. We have infinitely many solutions. We can also have one solution, but it turns out we could also have no solutions. And there's a few ways to do this. So these 2 planes that I've drawn, it's kind of hard to see, but they're parallel. Right? So I could have 2 linear equations that represented parallel planes that never intersect. So that means that there can't be any points that make them both true at the same time. But maybe more interestingly, I can add a plane to this picture that's not parallel to either plane, but such that they'll all never intersect. So if you kind of rearrange this, you can see that there's kind of this almost triangle cross-sectioned infinite prism, or whatever you want to call it, in between these planes. So they're not parallel. They each intersect pairwise, but we have no solution. So I want to summarize this, because this is one of the take-home messages of what I wanted to get out of this video, is how many solutions can we get from a linear system? And so the first point, a linear system always has no solutions, infinitely many solutions, or exactly one solution, is the biggest take-home message. These are the number of possible solutions. In particular, you can't get 2 solutions or 5 solutions. If you have more than one solution, there are infinitely many. But also of interest, if a linear system has fewer equations than variables, it can't have exactly one solution. It either has no solutions, like those 2 planes that were parallel, or infinitely many, like those 2 planes that intersected in a line. What this is, in my mind, saying is that in order to narrow things down to a single solution, we need as many pieces of information as variables. And then finally, if we have at least as many equations as variables, so for instance, in 3D, if we have 3 or 4 or 10 equations, we could have no solutions, we could have infinitely many solutions, or we could have exactly one solution. Any of these options is possible. So what's left, and this is already kind of a long video, I mean, we covered a lot, but I haven't talked at all about how do we even find these solutions, right? I drew some graphs and I put some points on them, but we're not going to, especially as we get to higher dimensions, be solving linear systems by drawing pictures. And so that's for a future video. That's the kind of the next step. Now that we know what linear systems are, what solutions are, and how many we might expect, we need to figure out how do we actually figure out what these things are.